Similar to the previous video, but this time we are going to integrate tan to the power of 4 secant to the power of 4. So the aim is to rewrite this in terms of this form, because we know that if we can get in terms of this form, we know it's going to be easy to integrate. So the trick is to break this up into two blocks, 1, 2. And then you can see that this thing here matches up with f prime, because secant squared is a derivative of tan. So the next step is to rewrite this thing here all in terms of tan, all in terms of tan, all in terms of tan. But the thing is, there's a block of secant squared here. To convert this block into all in terms of tan, we would make use of this identity. I will explain this identity in another video, but for the time being, just accept it. Accept this for the time being. So to convert this, we would put this block into here. So now this block here will become this. So this whole thing here will then become this, and then you can see that this is your f prime, and then everything here is all in terms of tan. Everything here is all in terms of tan. Then we know it's easy to integrate. If we can get into this form, we know it's going to be easy to integrate. So let's integrate it. So now integrate it. Let u equals tan of x. So du equals this thing here. So now this is exactly the same as this. So we can put du into this block here. And then put u into tan, so this whole thing here will become this. Multiply this out, that will then give you this, and then integrate, that will then give you this. So earlier we said let u equals tan, so we can put tan back into the u, and then it will then become this. So this is your final answer. So let me recap. Hang on. So to integrate something like this, we would make use of this identity. We would put this into here, and then everything here would then become in terms of tan, and then this is the exact derivative of tan. So we can convert this into this form. So cast your mind back a few videos. We did something similar to this. To integrate sine squared x cos to the power of 4x dx, we would break this into this and into this, and then we need to this is your f prime, and then we need to rewrite everything in terms of sine, but then there's block of cos squared here. So to convert this, we would make use of this identity. Though the point is that this identity here allows you to convert this into tan, but don't forget, you need a squared in order to do it. If you have to the power of 3, then you've got to use a different technique. But for the time being, we're just looking at when it's even. So even if you look at this, if you have cos to the power of 4, you can rewrite as cos squared x to the squared, and then you can make use of this to convert it all in terms of sine. But the point is that this identity here allows you to convert this block into tan. The point is that if you make use of this identity, you can convert this block into a block containing sine only. In the future, forget about this for the time being. In the future, this identity allows you to convert cosecant into cotangent into a block. But the thing is, this identity allows you to convert back and forth here. This identity here allows you to convert this back and forth between sine and cos. This identity here allows you to convert between secant squared and tan. So our next task is to try and understand where these identities come from. Okay, as it turns out. So in the next video I will explain why. But roughly speaking, if you look at the unit circle of radius 1, we've seen this before. If you draw a vertical line down here, this length here is 1 because it's radius of 1, circle radius 1. The height here is sine. The across here is cos squared, cos x. So you can use Pythagoras to come up with this. Now this thing here, if you look at the same circle of radius 1, but take the tangent right here, let's say this angle here is x. As it turns out, if you look at this triangle here, it's a right angle triangle because of the tangent line. This bit here must be a right angle here. Well, as it turns out, this length here is tan of x, whatever the angle is, and then it turns out that this length here is secant of x, which I will explain in the next video as to why this is x and this is secant. Well, if you use Pythagoras, the longest length, the hypotenuse, is this thing here. The adjacent, hang on, sorry, let me think. The hypotenuse is this. Don't forget our angles here. The opposite is this thing here, and then you've got your adjacent here, which is 1. And then as it turns out, if you look, well, don't forget this is a tangent line. This would be 90 degrees. If you look at this triangle, it turns out that this line here, this length here, is cotangent of the angle, whatever the angle may be, and then this length here would be your cosecant of x, and then, well, the radius stays the same, it's of length 1. So now, if you look at the, well, don't forget this is 90 degrees here. It turns out that, well, I will explain why in the next video, but if you use Pythagoras, this is your longest length here. This is your longest length here. So you can apply Pythagoras again. This is this bit here, and the radius is of length 1. So that's this thing here. So all these identities comes from this circle here, which I will explain in the next video. Okay.